All right. So this section is on graphs of equations, and I realize some of this is going to be pretty basic. I mean, we talked about how to plot points before, and that's something you're really familiar with. But one of the things in math that we need to get used to is if we have an equation, that equation actually makes a shape. Now, I realize that nearly everybody in here knows exactly what shape this is going to make, but we're going to run through just some quick ideas here. So one way that we can graph an equation is we can make an XY table, and we can start picking x's to plug in. Normally, x is what we call the independent variable. It's what we get to choose. We plug that in, and then we solve for whatever y is. So in this case, this is set up really nicely. This is in a real graph-friendly form. So if I plug in a -1, I put it right there. So this would be 2 times -1 plus 1. So that's going to be -1. Correct me if I make a little arithmetic mistake. Okay. If I plug in a 0, I take the 0 times it by 2 and then add 1. So I'm going to get 1. Plug in a 1, 2 plus 1, so that'd be 3. Plug in a 2, 4 plus 1, so that'd be 5. Okay. Now, I only plugged in 4 numbers for x, and I got 4 corresponding numbers for y. I'm going to come over here and I'm going to plot those. So I've got -1, -1, 0, 1, 1, 3, and 2, 5. And then what we normally do is we normally connect those. Now, with only 4 points, that may or may not be enough to draw an accurate graph. On this particular one it is, because this shape is a line, okay? And the name we give this, it's called a linear equation. It's called a linear equation because we get a line when we graph it, okay? Because the graph's in the shape of a line. Okay, now another thing that I want you to be aware of that isn't always talked about very much. This right here, you'll notice that we only graphed this point, this point, this point, and this point. And yet we filled it in between each one of these sets of points. And then we had arrows going off in each direction. Okay? Okay, what those arrows indicate and what filling in those little gaps in between those points indicate, that this right here is a picture of every single point that works in the equation. We only found 4 points that make the equation true. This right here is a picture of every single point that makes the equation true. So it is a picture of the points that work in the equation. So the reason this point right here is on the graph is because it makes the equation true. But let's take this point right here, -2, -3. Let's find that one, -2, -3. That would be about right here. That's not one of the points that we graphed originally, but does it work in the equation? How do you tell? Because, okay, we could plug it in. That would be one thing. Another way to tell would be it's on the graph. If it's on the graph, it's got to work in the equation. Same with this point right here. That's not one of the ones that we did originally, but it's on the graph, so it would work in the equation. So does that one work in the equation? Yes, it does. How can we tell? It's on the graph. It's on the graph of the equation. It's on the graph of that linear equation. What about 1/2, 0? 1/2, 0 is right here. The answer to that is no. And how do you know it doesn't work in the equation? Not on the graph. It's that simple. Okay? Now, we work with linear equations quite a bit, and we'll actually study those in the next section also. But linear equations are not the only thing that we'll be graphing. Okay? So there's an example right here. Again, we can plot some points on this one just to figure out what it looks like. Or you may already know what it looks like. Usually, if we're going to come up with roughly what a graph looks like, we're going to pick some points that are relatively easy to plug in. So we'll usually plug in 0, because that's an easy number to work with. And then we'll usually pick points around the origin. Okay? We usually don't get problems, at least introductory problems, that are way off in quadrant 1 or quadrant 4 or something like that. So we'll plug in a 0, maybe a -1, a -2, and then a 1 and a 2. If I plug in 0, again, that's the easiest one to plug in. 0 squared is 0 minus 1 would be -4. So I've got that point. If I plug in a 1, Again, what happens on this one is different than the previous problem. I don't multiply it by 2, I square it. I multiply it by itself. So I get 1, and then I subtract 4. So this is going to give me -3. Then I'm going to plug in a 2. Square it, I get 4. Subtract 4, I get 0. Now, the interesting thing about this particular one is what happens when I plug in a -1 instead of a +1? Tammy? Still positive. So I get a +1 again. I subtract 4, so I get -3. And then the same thing happens when I plug in a -2. I square it. I get a +4. Subtract 4, I get 0. So if I plot these points, clearly there is something different going on this one than there was on the last one. Now, if I just graphed the two of these, everybody watching? If I just graph the two of these right here, it might look like a line. Okay, but that's not quite on the line. Or we could kind of cheat and say, gosh, maybe it looks something like that, but that doesn't hit all of them. Clearly, there's something different going on with this shape than there was with the shape above. Okay, this particular one happens to be a curve, and what do we call this curve? We call that curve a parabola. It's the graph of a quadratic function, is what we'll learn later on in this chapter. Okay, but my point here is we can get a rough idea of what the shape is, and both of these graphs were graphs that you're probably familiar with, but we can get some idea just by plotting points. Okay, but is plotting points a very good technique? Is it a very efficient way of finding out exactly what the graph looks like? Okay, usually not. It's usually not. Okay, what are the drawbacks to plotting points? Can anybody think of one reason why plotting points is kind of a pain? Raymond? Okay, one mistake, and I'll just put ... If you make one mistake, so let's say I made an arithmetic error, and I got that this point should have been down here. Then I'm in real trouble, okay? Because that doesn't look anything like what it's supposed to. You make one mistake when you're plotting points, and you've got the wrong graph, okay? What's another thing that's tough about plotting points? Tara? Okay, it takes time. It takes a long time. And anything more complex than, say, a quadratic, a parabola, or a linear equation, or any basic function, it can take a long time in order to get what the shape looks like. Okay? You could guess, gosh, maybe it looks like this. Plot another point. Oh, that's not it. Take another guess. Not quite. It can take a lot of time to hone in what we're after. So it's going to be important in this class. We're going to develop a whole library of functions and equations where we know what shape they make just as well as we know what a linear equation looks like, or just as well as we know what a parabola looks like. Okay? Now, one of the things that can improve the graphs that we make is we can graph a couple of points. Okay? X-intercepts and Y-intercepts. Okay? So just to be clear, what are X and Y-intercepts? What's an X-intercept? Where it crosses the x-axis, and a y-intercept is where it crosses the y-axis. It's that simple. So let's take a look at these particular graphs right here. Okay, here's a y-intercept, here's a y-intercept, and here's a y-intercept. Okay, now what do you notice about each one of these y-intercepts, even though the axes are not scaled? Well, this one is kind of a parabola that opens up. This one looks a little bit, maybe not quite like a parabola, but kind of. What do you notice about the y-intercepts themselves? What's that? In this particular case, they're positive. Notice anything else? What if I asked you this? Even though the axes are not scaled, can you tell me something about the coordinates? X is 0, okay? Because it's on the y-axis, the x coordinate has to be 0 because you didn't go right or left. So that's got to be 0, comma, something that's positive. Okay, this has got to be 0, comma, something that's positive. That's got to be 0, comma, something that's positive. Maybe not as positive as that one. But every time we have a y coordinate, a y-intercept, the x coordinate is 0. So they're all 0, comma, whatever the y coordinate is. Okay? Well, what about all of these x-intercepts? Y is 0. Okay? So on every one of the x-intercepts, the y-coordinate is 0. So I ask this a lot to my classes. I even ask my calculus classes, and sometimes I'll have a student that I'm not quite sure, can't summarize how you find x and y-intercepts. Okay, so here's what I tell them to do. Make a little XY table like we had up above. If you plug in a 0 for x, that's going to tell you the y-intercept. If you plug in a 0 for x, or sorry, for y, that's going to tell you the x-intercept. Okay? So I'll say that probably quite a lot throughout the year. How do you find x and y-intercepts? Make a little xy table, plug in a 0 for x, that'll find the y-intercept. Plug in a 0 for y, that'll find the x-intercept. It seems a little bit backwards that if you want to find the y-intercept, you plug in a 0 for y, and if you want to find the x-intercept, I said that backwards, didn't I? Okay. So if you want to find the y-intercept, you plug in a 0 for x. If you want to find the x-intercept, you plug in a 0 for y. Okay. Just think about which axis you want it on and which coordinate would need to be 0. Okay. So we can look at the examples up above, or at least one of them. If I wanted to find the intercepts, find both of them. Okay. Usually the y-intercept is a piece of cake to find. If you plug in a 0, what do we get out of here? -4. Okay. If I set it equal to 0, that's a little bit more difficult. So I get 0 equals x squared minus 4, and then I'm hoping somebody can help us out with this. It's plus or minus 2. There are a couple different ways that you can solve that. You can move the 4 over and take the square root of both sides, or if we're really good at factoring, which we better be, you can factor this to x minus 2 and x plus 2, and then solve it like you would any other quadratic or any higher order polynomial that has a bunch of factors. So 2 out of that one and a -2 out of that one. So we actually get, we actually get 2 x-intercepts on this one. And does that match with what we saw up above? 2 x-intercepts right here at -2, 0 and 2, 0. And this one right here at 0, -4. So we got all those. Okay. Any questions? Okay, this one is not the same. Okay, this one is different. So if you plug in a 0 for x, what do you get for y? Very good. Okay, that's what you'd get. That's the equation. And then when we take the square root, when we put a square root in a problem, we have to account for the fact that we don't know whether that y was positive or negative to begin with. Because when you square it, it's always going to end up to be positive. So we'd have a +2 for one y-intercept and a -2 for another y-intercept. And then if you plug in a 0 for y, that one's a little bit easier. Plug in a 0 for y, 0 equals x plus 4. So what is the x-intercept? -4. So let's just take those 3 points. Any ideas on what this would look like? Okay, I see a bunch of people doing this. It is a sideways opening parabola. Okay, and some of you may be aware of some of the problems with sideways opening parabolas. You may have graphed some of those before. We'll talk about that. Okay. All right. So that's x and y intercepts and a little bit about basic graphing. Another thing that we can use to graph equations or make graphing equations easier, more accurate, less work and that sort of thing is we can use symmetry. Okay. So we're going to talk about 3 different types of symmetry that can work with equations. Okay. So we're first going to talk about symmetry with the y-axis. Okay, I've got an example of a graph that's symmetric with the y-axis. Okay, it's y equals x squared. It's just a regular old parabola. Okay, this type of symmetry is sometimes called reflective symmetry. Okay, and the reason it's called reflective symmetry is the graph looks the same when we reflect across the y-axis. Occasionally, this is called line symmetry or fold symmetry. Because what we can do is imagine taking your paper and let's fold it right along that axis of symmetry, right along the y-axis. The left looks the same as the right looks the same as the left. They are mirror images of each other. Okay? If we folded it, one would lie right on top of the other. Okay? So the right side looks the same as the left side. That's reflection across the y-axis. Okay, now on this particular graph, if we take a look at it, if I were to go over to 2, if I plug in a 2, I get a 4. What happens if instead of going to the right 2 from the origin, I go to the left 2? What do I get here? Negative 2, 4. I get exactly the same y value. So even though I went to the left instead of the right, I got the same y value. And that even happens here. If I go over here 1 unit, I go up 1 unit, because that would be 1 squared. If I go back 1 unit, I go up 1 unit, because that would be negative 1 squared. Okay, so it doesn't matter whether I go to the left or the right, I get exactly the same function value. So we can generalize this. Okay, remember, that's what we want to do, is we want to come up with ideas or ways of stating this fact in general. So what we can say is, if xy is on the graph and it's symmetric with the y-axis, what other point would also be on the graph? Okay, change the sign of the x-coordinate, and it would have the same y-coordinate. Doesn't matter whether you go to the left or the right, you get the same y-coordinate. Okay? Any questions? Okay, so now I've got one that's symmetric with the x-axis. Okay, again, also called reflective symmetry. It's called symmetric with the x-axis because when we fold it along the x-axis, then what would it be in this case? Before it was right and left look the same, now it's going to be what? Top and bottom. Okay, top looks the same as the bottom. So here's our example right there. And what this means is, and what we want to take note of is, for the same x value, we get different y values. Same y value, but different sign. Okay? So if we go to 4, if I go to 1, 2, 3, 4, if I go to right there, and I go up to this point and down to this point right here, this upper point would be 4, 2, and this one would be 4, negative 2. Okay? And notice, they're just reflections across the line, y equals 0, or the x-axis. And we could generalize that idea by saying, if you know xy is on the graph, which coordinate changes sign? The y-coordinate does, okay? The top goes to the bottom goes to the top. So we just change that sign. So this is going to be x, negative y. Okay? Now, we haven't covered this yet, but maybe you know this. We don't use symmetry with the x-axis very often. Can anybody tell us why? It's not a function. Okay? It's not a function, and we're going to talk about what a function is in the next section, and we'll cover that some more. So let's talk about symmetry with the origin, because this is one that is used quite often. Okay? So symmetry with the origin is called rotational symmetry, and it's called that because the graph will look the same when it is rotated 180 degrees about the origin. So I can't do this up here, but you can on your paper. I've got an example of a graph that's symmetric with the origin. Okay? Y equals x cubed is symmetric with the origin. If I were to put my pencil right at the origin and then turn the paper 180 degrees, would it look exactly the same? Spin that around. It does, doesn't it? Okay? That's what we mean by symmetry with the origin. It is not a fold or reflective symmetry. Okay? It's a rotational symmetry. So you have to hold one point exactly where it is and then rotate 180 degrees. Okay? All right, now let's get some points on here. If I plug in a 2, that point would be up here and its coordinate would be 2, 2 cubed, which is 8. If I plug in a negative 2, now if I plug in a negative 2, I've got 3 negatives. What's the sign of the answer? Negative, and 2 cubed again would be 8. So this point right here is negative 2, negative 8. So you'll notice what happens on this one. Okay? It's not symmetric with the y-axis, and it's not symmetric with the x-axis. We're not switching right and left and top and bottom. We're rotating this whole thing around. Okay? And notice what happens. 2, 8 is on the graph, so is negative 2, 8. So we could generalize that by saying if xy is on the graph, there should be another point that's also on the graph, and what is that point? negative x, negative y. They both changed. Okay? Now, I want you to watch something here. What if I did this? What if I took this right here, this shape right here, and what if I reflected it across the y-axis, like this? This would be negative 2, 8, right? What if I then reflected it across the x-axis? What if I flipped it down here? It would be negative 2, negative 8. So you can actually accomplish symmetry with the origin by doing two reflections. I could reflect across the y-axis, then across the x-axis. Okay, or I could reflect across the x-axis, then across the y-axis. If I flip it down here and then over here, like that. Okay. We don't often think of it that way, but you could accomplish the same thing. Okay, are there any questions? Okay. What if somebody went to all the work of figuring out what the graph looked like on this side, on the left side of the y-axis, and then said, you know what, I know this graph is symmetric with the y-axis. Could you graph the rest of it? Piece of cake. Just reflect it over here, and that's what it would look like. What if they went to all the work to figure out, you know what, I know that on this side over here, on the positive side of the x-axis, it looks like this, and it's symmetric with the origin. Could you graph the rest of it? Well, let's think about this for just a second. This point looks like 1, negative 1. 1, negative 1. If it's symmetric with the origin, where would that point be if I reflected it? Or, sorry, rotated it? Negative 1, 1, it would be up here, okay? So it's going to look something like this, okay? See how if we turn that 180 degrees around the origin, it looks exactly the same? And then what if this was symmetric with the x-axis? Top should look the same as the bottom, so it would look something like this, okay? So I know there were some complaints about the amount of homework. You have a couple problems where that's what you do. That's not too bad, right? Okay. So we just need to make sure that we understand what the symmetry is that we're talking about, okay? Now, on these graphs right here, looking at a graph and figuring out what type of symmetry it displays or completing the graph based on the type of symmetry that you know it has is not a very difficult task. Looking at an equation and figuring out, how did they find out that without completing the graph, they know that it's symmetric with the y-axis? That is a more difficult algebra type of skill, okay? So here's what we're going to do. I've written down on this page, this is a test for symmetry. You can check for symmetry with the y-axis, the x-axis, or the origin, okay, by starting off this test the exact same way. And here's what we're going to do. We're going to replace each x with a negative x. This is trading, if you wanted to think of it, right for left and left for right. We're going different directions on the x-axis. Then we're going to simplify. If we get the exact same thing as we started out with, the exact same equation, then it's symmetric with the y-axis. So if it's the exact same, it doesn't matter whether you go to the left or the right. You get the same thing. That's what symmetric with the y-axis means. Okay? Doesn't matter whether I go here and I end up at 4, go here and I end up at 4. The point is they would be reflected across the y-axis. Okay? The test for x-axis symmetry looks the same way. Or sorry, replace each y with a negative y. So instead of changing right for left and left for right, what are we doing right here? Changing top for bottom. So if you change the top for the bottom and you get exactly the same thing, then it's symmetric with the x-axis. Okay? Top for bottom, symmetric with the x-axis. Right for left, symmetric with the y-axis. Okay? And what if we wanted to do symmetry with the origin? Take a look here. What are we going to replace? Yeah, doesn't matter if you change right for left and top for bottom. If you simplify it and get exactly the same thing, then it's going to be symmetric with the origin. Okay? What if none of those work? Then there's no symmetry. No symmetry at all. Okay? Now, you do need to be a little bit careful. I've picked relatively easy problems, except for maybe this one right here. Okay, so let's run through here and let's check for symmetry. So we want to check for y-axis, x-axis, and origin. Let's think for a second. Symmetry with the y-axis. We're trading left for right. What variable goes in this direction, left to right? X. So we're going to change the sign of the X. And you'll notice that up above I wrote them in parentheses. It's a good idea to plug them in parentheses here. If I simplify this, I get y squared equals, whoops, negative x plus 9. Is that exactly what we got to start with? Nope. Answer there's no. It's that simple. Just a little bit of algebra, and we're there. Symmetry with the x-axis. We're trading top for bottom. Which coordinate goes up and down, top for bottom? Y. So this is going to be negative y squared equals negative x, or sorry, x. Back to the original one, x plus 9. And I get y squared x plus 9. Exactly the same? Yes. So we know for a fact that that's going to be symmetric with the x-axis. And you can almost tell, is that going to be the same? This one's going to be y squared. It's going to look the same as that one up above. So the answer there is no. The only type of symmetry that this would display is symmetry with the x-axis. The top would look the same as the bottom. We couldn't rotate it around the origin. We can't change the left for the right. Okay, let's do this one. Changing the x. Okay, now, is it okay if I just do this mentally? What happens if I plug in a negative x and square it? X squared plus 9. The bottom's going to be a negative 3x. Is it exactly the same? Nope. Let's plug in a negative y. Negative y equals that stuff. Yes or no? No way there. Okay, what if we do this? Negative y, negative x squared plus 9, negative 3x. So here's what I've got. Negative y equals x squared plus 9 over negative 3x. Is that exactly the same as what we started with? Is it simplified? Peyton says no, it's not simplified. Okay, how do you simplify this? Yeah, divide both sides by negative 1, or it might be easier just to multiply by negative 1. Multiply both sides by a negative. What's that going to do to the negative y? Positive y. And I'll just multiply the bottom by a negative. So I have a positive y equals x squared plus 9 over 3x. Okay, is that the same thing as we started out with? It is. Or another way that you could think of this is we had negative y equals x squared minus, excuse me, that was a plus 9. Negative 3x. There are three ways to write a negative fraction. Okay, if you don't remember this, okay, you can write negative 3/4 as negative 3/4, negative 3/4, and negative 3/4. The negative can go on the top, out front, or on the bottom. Okay, where is it right here? It's on the bottom. Well, let's move it out front, and then let's multiply both sides by a negative. That's basically going to change the sign of both sides. So we get right back where we started. So yes, on the origin. Okay, it would be symmetric with the origin. Not with the x-axis, not with the y-axis, but with the origin. Okay, and then let's take a look at this guy right here. Let's think for just a second. If you plug in a negative x and square it, what are you going to get? You're going to get a positive x squared, right? So what about y-axis? Yes. What if you plug in a negative y? Square it. Positive y squared. So that's going to be yes. And what if they were both negative x here, squared, negative y here, squared? Answer there is going to be yes. This has all three types of symmetry. Okay. Does anybody know what that looks like? Very good. Very good. Nice job, Cameron. Okay. And we'll actually see that a little bit later. Okay. Any questions? Okay. So this one says, and you've got some problems on your assignment like this, it says, use symmetry and intercepts to graph the equation. Okay. So let's check symmetry first. So if I checked symmetry with the y-axis, is that a yes or a no? It's the same problem as right above. That's why it's got a star by it. Okay. So this was a no and a no. A yes on symmetry with the x-axis. So if I can figure out what the top of this looks like, so let's plug in 0 and above for y. So let's do a little xy table, but let's plug in y's rather than x's. So I'm going to plug in 0, 1, 2, and 3. If I plug in a 0, what's x? -9. Everybody got that? See why it's -9? You'd have 0 equals y, x plus 9, so you'd move that over. In fact, how about we do this? Since we're solving for x on every one of these, why not put it in a format where the equation is already solved for x? Now plug in a 0 for y, immediately see the -9. Let's plug in a 1 for y, -8. Plug in a 2 for y. 2 squared would be 4, 4 minus 9, -5. Plug in a 3. 3 squared is 9, minus 9 is 0. Now, I want you to look at this, and can somebody tell me something about these guys right here? Those two that are highlighted in yellow. They're intercepts, okay? If the y is 0, that's the x-intercept. And if the x is 0, that's the y-intercept. Okay, so let's come over here and sketch. This is going to be the top part of this because all the y's are 0. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. We're right here. -8, 1. -5, 2. 0, 3. And we could label each one of those. And if we know what the top looks like and we know that it's symmetric with the x-axis, then we know what the bottom looks like. The bottom's got to look like this also. And can you tell me what this point right here is? Which one is it symmetric with? If this one is 0, 3, what's this one? 0, -3. Okay, and this one right here was -9, 0. Okay, so there's our graph. We only graphed these 4 points, or we figured out what those 4 points were. Okay, and then we could just plot the reflected equivalent of each one of those. Any questions? Okay, raise your hand if you've seen stuff like that before. Excellent. Okay, would you go ahead and graph this one? Once you get done, check with your neighbor, make sure you got the right answer. What should we probably check for first? Probably symmetry. Okay. Is there any symmetry here? Okay, if you take a look at y-axis, you change the x to a negative x. That would still be negative x squared, and this would be a positive 2x. Nope. Symmetry with the x-axis, change the y. Okay, the other ones are just what they were before, so there's no on that one. And what about origin? Okay, you'd have a negative x. Whoops, that should have an x on there. Okay. A negative y here. This would still be negative x squared, and this would become a positive 2x. Is there any way to simplify this and make it look exactly like it was before? No. So is there any symmetry here? Okay. Anybody got it graphed yet? Got it? How'd you do it? Okay. Okay. So there's no symmetry with the origin or the x-axis or the y-axis, but it is a parabola. Parabolas always have some sort of symmetry with themselves because the left side's the same as the right side. How did you figure that out? Okay. So I'm gonna show the work up here. Did you do an XY table? Okay. So XY table, you plugged in -2. Okay. Not a bad place to start, right? And what did you get when you plug in a -2? Okay. So if we plot these points, and the hard part about this is, let me make my axes a little bit bigger. The hard part about this is if I'm at -2 and 0 right there, and then -1, 1, and then 0, 0, the next point is 1, -3, and then the next one after that, I've got to go all the way down here to get to that point 2, -8. Okay, now did you just guess from there, or what else did you do? Okay, Cameron knows that, whoops, where are we? Cameron knows that x squared is always going to be a parabola as far as the shape goes. He said, well, gosh, if I can see the turn, then I'm in good shape. What if you only did this? Okay, everybody watch, please. What if I erase that? What if we started at 0 and just kept plugging in points? Like, let's say I plugged in a 3. I'd get, where are we here? This would be -9 minus 6. So the next one would be -15. It would be way down here. If you looked at that on this particular graph, what does it look like that is? Does it look like a parabola? Okay, here's the important part. Cameron happened to pick points, and I gave you a graph where an important feature on the graph occurred near the origin, near these nice points that we normally plug in, around 0, positive and negative. Okay? But if you only pick these points, you can be misled into thinking, gosh, this looks, I mean, on my graph, it kind of looks like a line, doesn't it? Okay, but this point right here and this point right here are really important, especially the second one right here, the one that's at -2. Because you could maybe reason your way into thinking, gosh, it's maybe curved something like this, but once it makes that bend and actually turns around, we know there's something interesting going on right here. What would be a good thing? Now, Cameron knew that this was an upside down opening parabola. What if you weren't sure if it was an upside down opening parabola? What would you do? Plug in -3. So let's see what happens if you plug in a -3. If you plug in a -3, guess what you get? You get -3. Okay? It is actually symmetric with that one right there. See these values that are kind of repeating here? It's this one right here. And then that's pretty darn good evidence that it looks something like this. Okay? Any questions? Okay. Here's what we're going to do. As we go through this, I gave you the calendar. I would love to go faster than what the calendar has. Okay? So we're going to be able to finish this partway through tomorrow. You have everything you need to get started on the assignment and do everything but the stuff that asks about circles. Okay? We'll do circles at the beginning of class tomorrow, and then we'll get started on 1.2. Okay? We may have some time for a few questions or something like that. What I need you to be doing is get on the homework, get the stuff done that we've covered, which is all the equations and symmetry and stuff like that. We'll cover circles at the beginning of class tomorrow, and then you can finish it up. This will be due on Monday. Okay? All right. Have a great day. Thank you very much. Again, if you've got a question, come and see me. If you know you have gaps, if you know there's something you need to practice from that chapter P, send me an email, tell me what it is, and we'll get you some practice material.